So in this lecture, we'll learn two very important concepts in computer architecture. It's the concept of clock and the concept of frequency of a processor. So let's get started with the concept of a clock. And to understand the concept of a clock, we'll consider a signal that is changing over time. And so we'll have on our x-axis here time, and here we have several different signals that we represent. This is a typical time diagram for a digital circuit. So we'll consider a very special signal, that's the clock. The clock is a signal that it can start either low or high because it is a constantly changing signal. And at some point, the signal goes, for example, from low to high. You can think that it goes from 0 to 1. And then it stays in 1 for a while. And then it goes back to 0. And it stays in 0 for a while and goes back to 1. The clock signal does that constantly all the time, and that's the only thing that it does. So it's a very regular signal that keeps changing between 0 and 1 at constant intervals. The time between two changes of the clock and two same changes, which means in this diagram I'm showing two changes from low to high. So the time between two consecutive changes from low to high in a clock signal is constant. And this time is called the clock period, is the time that it takes for the clock to go through a full period from having made the transition from low to high, staying high for a while, make a transition to low, and then making the next transition to high. So during this time, the clock has gone through a full period, and this is called the clock period. Now, we want to consider the data transfer and the computation that happens in the processor. That data transfer, that is the time for the data to go from one of the subunits in the processor to another of the subunits of the processor, or the time for a computation to take place, such as, for example, an addition inside an arithmetic and logic unit, that happens during the clock period. So in the middle of the clock period, either the computation is happening or a signal is in transit between two units in the processor. And at the transition of the clock, there is an update of the state. For example, if you are computing an addition, the addition will be computed during the clock period, and whatever is the destination of that adder will be updated at the transition of the clock period. So this will be the process for computation inside a processor. The clock period is the duration of the clock cycle. Those two things are the same, they are synonyms. And you can think on, for example, one example of a clock period would be that it lasts 250 picoseconds. This is the same as saying that the clock period lasts 0.25 nanoseconds, or that the clock period lasts 250 times 10 to the minus 12 seconds. 1 picosecond is 10 to the minus 12 seconds. 1 nanosecond is 10 to the minus 9 seconds. Another way to refer to the clock frequency is to talk about the clock rate. Those two things are also synonyms. Sometimes we say clock frequency, sometimes we say clock rate. They mean exactly the same thing. The number of clocks per second is what we know as the clock frequency or the clock rate. So how many of those cycles that I'm showing the diagrams happen in 1 second, that will tell me the clock frequency. For example, you may have heard that a given processor runs at 4 gigahertz. Let's see what it means. What does it mean to say that the processor runs at 4 gigahertz. It is the same to say that it's 4,000 megahertz or 4 times 10 to the 9 hertz. So it means that there is 4 times 10 to the 9 clock periods happening during 1 second. So let's talk about frequency now. Again, I have time, and now I have represented my clock signal here with in a smaller scale, but it's the same thing as before. The time between two transitions is constant, and remember that the clock is happening forever. So at some point, I'm going to start measuring time. So we start measuring time in a transition of the clock, and I'm going to finish measuring time in another transition of the clock. In this case, I'm measuring from a transition from high to low to another transition from high to low. And the question that I want to know is what is the number of CPU clock cycles that has happened during the time that I was measuring? And let's say that I have been observing and I have seen 40 billion cycles happening during this time. Then the next question is, how much time has passed during the time that I was measuring? So I have observed 40 billion cycles, but how much time did it take for me to observe the cycles? And let's say that it was 20 seconds. So I have observed 40 billion cycles in 20 seconds. So the frequency is the number of clock cycles per second. So in this case, we can calculate the frequency as the number of clock cycles that we have observed, which was 40 billion, divided by the time that it took for us to observe that many cycles. It was 20 seconds. When I divide these two numbers, I will find out that the result is 2 times 10 to the 9, and the unit will be cycles per second, because I observed 2 times 10 to the 9 cycles in each second. This is what gigahertz means. So when I say that a processor runs at a frequency of 2 gigahertz, I'm saying that in that processor there will be 2 times 10 to the 9 seconds cycles in each second. Another question that I may ask is, what was the clock cycle time or the clock period? So how long did it take, given this measurement that I just did, where I measured 40 billion cycles in 20 seconds, I can now compute how much time did it take for me to have 2 of those consecutive transitions, either from high to low or from low to high, but I want 2 consecutive transitions in the same direction. So this is the question that I'm asking now is, what is the duration of a single clock cycle? And again, I can compute that. The duration of a single clock cycle will be given by the time that it took for me to measure, divided by the number of cycles that I have observed. So if I divide the total time by the total number of cycles, I will have the clock cycle time. And the clock cycle time then will be 0.5 times 10 to the 9. And the unit will be seconds per cycle, because that's the amount of time that it takes for each one of the cycles. So now we have reviewed how to measure frequency and how to measure clock cycles. The other way that I can express this time is to say this is 0.5 nanoseconds, because 1 nanosecond is 10 to the minus 9 seconds. So let's look at the relation between clock cycle time and frequency. So the frequency was 40 billion cycles in 20 seconds, divided by 20 seconds. The clock cycle time was 20 seconds divided by the 40 billion cycles. So the clock cycle time is the inverse of the frequency, is 1 over the frequency. So here's an example of the beginning of a question that appeared in an exam in 229 in the past. And the question starts saying, the current processor commercialized by TinyProc Inc. is the TP500 that runs at a 500 megahertz frequency, and the exam said that 1 megahertz is equal 10 to the 6 hertz. So what is this part of this question telling me is that I have a clock running at 500 megahertz frequency. So from that, I can compute the clock cycle time. All I have to do is to do 1 over the frequency. So 1 divided by 500 times 10 to the 6 is equal to 2 times 10 to the minus 9, which means that the clock cycle time for that processor was 2 nanoseconds. This is just an example to illustrate situations where you're going to use what you just learned, that is the clock cycle time is the inverse of the frequency. You often are going to need that to solve some questions that you may see either in homeworks, quizzes, or in exams. But now, because we know algebra, we can use the fact that we know that the clock cycle time is 1 over the frequency to substitute in this equation. Well, the CPU time to execute a given program will be given by the number of CPU cycles that I need to execute the whole program times the clock cycle time. So if I multiply the time that it takes for one clock cycle by the total number of clock cycles that took to execute the program, that will give me the time to execute that program in seconds. But because we know algebra, we can replace the clock cycle time here by 1 over the frequency. So we can see that the CPU time to execute, so the time to execute a program in the CPU is the number of CPU clock cycles divided by the frequency. Which implies that if I have fewer clock cycles, I have better performance, because of course then it takes a shorter amount of time to execute the program. And if I have a faster clock, then I also have better performance. So some of you may have heard about the term overclocking your CPU. That means you are increasing the clock frequency of your CPU to get better performance. So let's look at an example of a calculation that comes from an exercise that may have appeared either in homeworks or in exams in the past. And in this example, I have a computer A and I have a computer B. The computer A can render an explosion. Remember the example with rendering an explosion for a movie from the previous lecture. So this computer A can render the explosion in 10 seconds and has a frequency of 2 gigahertz for execution. Now, the designing team says that running that explosion in 10 seconds is too much time. They have a goal that they need to render the explosion in 6 seconds. So we are now designing this computer B. And the question to the design team is, can you make that explosion be rendered in 6 seconds? And the architecture team says that I can build a computer with a faster clock, but this computer will have to execute 1.2 times the number of clock cycles that the computer A executes to do the same computation. This commonly happens in computer architecture, that when you increase the clock frequency in the design, you end up needing more cycles, because instructions that could finish in one clock cycle before, when the clock cycle got smaller, can no longer finish in one clock cycle and they will need a second clock cycle. So on average, this computer B will need 1.2 times as many clock cycles as the computer A. So let's see how we solve this problem. The question that the problem is asking is, what should be the frequency of computer B if computer B is to reach the goal of completing the rendering of an explosion in 6 seconds? We'll take the relation that we know that the clock rate of the computer B will be the number of clock cycles that I need to execute to render that explosion in computer B, divided by the CPU time of computer B. Well, I know that the number of clock cycles that computer B is going to have to execute is 1.2 times the number of clock cycles that computer A will have to execute. And I know that the CPU time of computer B has to be 6 seconds because that's the goal that was given to me by the graphics designing team. Well, the number of clock cycles of computer A is the CPU time of computer A times the clock rate of computer A. Well, I have this data. I know that the CPU time of A was 10 seconds and the clock rate of A was 2 gigahertz, what is 2 times 10 to the 9 hertz. Therefore, I know that the number of clock cycles of computer A is 20 times 10 to the 9 cycles. Well, now I can replace the relation that I have for the clock rate of B. I can replace the number of clock of cycles A that I just found out in the relation that I have for the clock rate of B. And that will give me, if I do the arithmetic correctly, a clock rate of, or a clock frequency of 4 gigahertz for computer B. So this is just an example illustrating how I can use the simple relations that I have learned in this lesson to make, for example, a prediction for the clock frequency that a given computer has to have, giving a goal for performance that was given to the designing team. So recapping this lecture, what we have learned in this lecture is that the clock is a very regular signal in your machine, and the time between two identical transitions of the consecutive identical transition of the clock is the clock period. We have learned that we can compute the frequency and we can compute the clock time, the clock cycle duration if we measure the total number of clock cycles and the time for a period of time. We have learned that the CPU time is the number of clock cycles divided by the frequency, and therefore if a program executes in fewer clock cycles, the performance will be better, and if I make my clock frequency higher, then the performance is always better. And we did a small example illustrating how we can use what we just learned in a problem to predict the performance that are going to need in order to achieve the frequency that are going to need in order to achieve a performance goal from the designing team.